Welcome to The Explainer. So, if you're a focused learner who is absolutely ready to master organic chemistry, well, you're in the exact right place. Today, I want you to put on your detective hat. We're going to be chemical detectives, and we're solving molecular mysteries by decoding the exact reaction mechanisms of haloalkenes and haloarenes. We'll be using actual handwritten source notes to uncover the clues, trace the movement of electrons, and predict outcomes just like the experts do. Let's get into it. Here is our roadmap for today. We are kicking off with the foundations of halogenated compounds, then looking at electrophilic aromatic substitution mechanisms and directing groups in benzene. After that, it's the big one, nucleophilic substitution, SN1 versus SN2. Then we'll cover stereochemistry, and finally, we'll wrap it all up by solving some complex reaction problems. All right, Section 1, Foundations of Halogenated Compounds. Now, you might be wondering, what makes these molecules so reactive in the first place? Well, the entire reactivity of these molecules hinges on the polar carbon-halogen bond. See, the halogen aggressively pulls electron density toward itself, which leaves behind a highly reactive, positively charged carbon. But how do we even get halogen onto a neutral alkane to start with? It happens through this amazing, cascading chain reaction that is triggered by literally a single photon of light. Step 1 is chain initiation. That light energy forces homolytic cleavage. It splits a halogen molecule right down the middle into two highly reactive free radicals. Step 2 is chain propagation. That radical attacks an alkane, creating a brand new carbon radical, which then turns around and attacks another halogen molecule, keeping the whole cycle going. Finally, step 3 is chain termination. That's when two radicals just happen to bump into each other, combine, and end the cascade. It's basically a brilliant, self-sustaining molecular domino effect. Moving right along to Section 2, electrophilic aromatic substitution mechanisms. I want you to think of the stable benzene ring as a chemical fortress. Its delocalized pi electrons make it incredibly resistant to normal addition reactions. It's tough. So to actually breach it, we have to follow 3 extremely precise steps. First up, the generation of an electrophile. We have to create a species so desperately electron-hungry that it can challenge benzene's inherent stability. Second is the electrophilic attack on the ring itself. This temporarily breaks that beautiful aromaticity and creates a positively charged intermediate. And third, the loss of a proton, which immediately restores that stable aromatic ring. A prime example of this from our notes is sulfonation. And sulfonation is super unique because based on the activation energies involved, it's actually an entirely reversible process depending entirely on the concentration of sulfuric acid you use. Okay, Section 3, directing groups in benzene. So once we finally have a substituent attached to our benzene ring, that first group essentially acts like a traffic cop. It dictates exactly where the next incoming group is allowed to attach. We can distill all the complex reaction mappings from the source notes into 4 golden rules. Rule 1, ortho and para-directing groups generally take precedence over meta-directing groups. Rule 2, if we're looking at electron-donating groups, or EDGs, the stronger donor, meaning the one pushing more electron density into the ring via resonance or induction, gets to dictate the position. Rule 3, for electron-withdrawing groups, the stronger one rules, assuming both are meta-directing. And Rule 4, this is the ultimate tiebreaker. An electron-donating group will always overpower an electron-withdrawing group when they are battling for positional supremacy on the ring. EDGs always win that fight. Which brings us to Section 4, nucleophilic substitution, the ultimate SN1 versus SN2 showdown. We've reached the critical mechanistic showdown that plagues organic chemistry students everywhere. The source material precisely delineates the rules governing this battle, so let's break it down. SN1 is a unimolecular 2-step process, and it relies entirely on forming a stable carbocation intermediate. It absolutely thrives with weak nucleophiles and polar protic solvents, think water or alcohol, because those solvents stabilize the charged intermediates. SN2, on the flip side, is a bimolecular, 1-step concerted mechanism. The nucleophile literally slams into the molecule at the exact same split second the halogen leaves. Because of that, it demands a strong nucleophile, and it heavily favors polar aprotic solvents, like acetone or DMSO, which don't build a cage around the nucleophile and slow it down. Let's think about how this actually looks thermodynamically. Picture an SN1 energy graph. It has 2 steps, right? So that dip, that valley right in the middle, represents the physical carbocation intermediate, just waiting around for the second step to happen. Now contrast that with the SN2 graph. It is just one massive activation energy mountain. That peak is a concerted transition state where bonds are breaking and forming simultaneously in one explosive, highly coordinated moment. All right, Section 5, Stereochemistry and Reaction Conditions. The really cool thing here is that these reactions, they don't just happen on flat, two-dimensional paper. They happen in 3D space, and their thermodynamic path drastically dictates the physical 3D shape of our final product. Because SN1 creates a flat planar carbocation intermediate, in that valley we talked about, the incoming nucleophile can attack from the top or the bottom. This gives us a mix of inversion and retention, which often leads to racemization. But SN2? SN2 is a strict backside attack. The nucleophile helps the exact opposite side of the leaving halogen. This strictly results in what the notes call a Walden inversion. The molecule literally flips.
Okay, let's put it all together in Section 6, Solving Complex Reaction Problems.
All right, detectives, here is your first actual challenge. If you have a series of substrates with different branching, I want you to pause and predict which one of these reacts the fastest via SN1 and which reacts fastest via SN2. Have a guess? Let's find out. So, breaking down the handwritten solution, for SN1, it is all about carbocation stability. Tertiary substrates, those are the carbons attached to 3 other carbons, form the absolute most stable carbocations because of maximum hyperconjugation, so they react the fastest in SN1, no contest. But for SN2, it is the exact opposite. Because SN2 requires that strict backside attack we just talked about, bulky tertiary groups physically block the incoming nucleophile. It's basically a path of least steric hindrance. Therefore, small, unhindered primary substrates react the fastest in SN2. Next question for our detectives. When you have a secondary substrate, which is kind of caught right in the middle, right? It's neither perfectly SN1 nor perfectly SN2. How do environmental factors, like your choice of solvent, act as the ultimate accomplice in forcing a specific reaction mechanism? Now, what's really interesting here is how beautifully absolute these rules are mapped out. If you have a 3-degree tertiary substrate, you are guaranteed SN1. A 1-degree primary substrate? Guaranteed SN2. But for that tricky 2-degree secondary substrate, the solvent is the absolute tiebreaker. A polar protic solvent will always force it down the SN1 path, while a polar aprotic solvent will strictly force the SN2 path. The environment literally controls the chemistry. Let's raise the stakes a bit. What is the spatial fate of a complex, 3D, chiral molecule when it's violently attacked by an incoming nucleophile in a specific solvent? Will it manage to keep its shape, or is it going to flip? If we trace the handwritten solution involving diastereomers, pay attention to a reaction using KOH in DMSO. Now remember, DMSO is a polar aprotic solvent, and as we just established, that strictly forces an SN2 mechanism. Because it's SN2, the nucleophile has absolutely no choice but to perform a backside attack. The result? A complete Walden inversion. The molecule's 3D configuration is flipped completely inside out. It's exactly like an umbrella being blown backward in a massive gust of wind. For our final case, let's look at a scenario that routinely trips up even seasoned chemists. What happens when our carbon neighborhood is just incredibly crowded, particularly on the adjacent or beta carbons inside complex cyclic structures? Even if the reacting carbon is primary or secondary, if the adjacent beta carbon has massive, bulky methyl groups hanging off it, like a neopentyl structure, it basically acts as an impassable physical brick wall. This steric bulk completely blocks an SN2 backside attack. It's just not happening. This forces the molecule to either undergo a complicated skeletal rearrangement, or it's going to require severely elevated temperatures just to get the reaction to proceed at all. Which brings us to the end of our investigation, and I want to leave you with one final provocative question. We've seen today that SN2 provides a 100% predictable 3D inversion, right? While SN1 gives you kind of a mixed bag of stereochemistry. So if you were a pharmaceutical scientist designing a life-saving drug where one specific 3D shape cures a disease, but its exact mirror image is highly toxic, which mechanistic pathway would you want to harness as your ultimate tool? See, mastering these seemingly abstract mechanisms isn't just about passing an organic chemistry test. It is the fundamental key to real-world molecular engineering. Keep questioning, keep analyzing those reaction pathways, and I will see you in the next explainer.